All right, are people ready? Cool. All right, we can start the stream then, and I'll get started. So this is, we're going to learn zk in 90 minutes. This is a collaborative workshop with the Mina protocol. This QR code will appear at the beginning of the presentation, throughout it, and at the end, and it links to a Notion page that has a bunch of relevant information, Discords, links to the GitHub, programs that we'll mention throughout the presentation, et cetera. So the idea being you don't have to worry about taking notes or jotting anything down. We have notes taken for you already, and you can just scan the QR code to get them. Oops, sorry. Again, if you haven't installed the zkApps CLI or cloned the repository, you can do that if you want to follow along. You don't have to if you just want to sort of watch and learn. OK, so who am I? I'm Jack Servia. I'm a developer relations engineer at O of One Labs. I'm based in Denver, Colorado. I was born in Denver, Colorado, and I plan to live here forever, basically. And that's my Twitter. OK, so what's O of One Labs? Who's building Mina? What's Mina Foundation, et cetera? So O of One Labs is basically a zero-knowledge technology company. We built the proof system for the Mina protocol and also the reference node implementation. Mina Foundation is more akin to the Ethereum Foundation. They do things like sort of steward the whole ecosystem. They have very cool programs that we'll talk about later on in the presentation. If you're looking for a grant or if you're looking to do something kind of big picture in the ecosystem, they're probably the people you want to talk to. So it's not just O1 Labs and Mina Foundation that are building Mina protocol, though. There's actually a whole bunch of companies, and I didn't include them in a slide because I didn't have time to reach out and ask if they wanted to be included in a slide and stuff. But we'll talk throughout the presentation about a couple of other organizations that are helping build the Mina ecosystem. So this is our agenda for today. First, we're going to talk about SnarkyJS, then the Mina protocol. Then we're going to do Hello Wordle. This is we'll walk you through building a Wordle smart contract using SnarkyJS. And then we'll talk about next steps and have questions and answers. So SnarkyJS is a TypeScript library for defining zero-knowledge proofs. And it's also the smart contract language for the Mina protocol. It looks like this. We don't have to worry about that quite yet, but we'll talk about it in maybe 20 minutes. Everything is in TypeScript, so you can keep using the tools that you're familiar with, like NPM, Prettier, VS Code with IntelliSense, and ESLint. And it's very easy to learn. You can see here, we've done a pretty good job of making sure that everything in the library has really good typedoc coverage. So if you want to learn SnarkyJS, you can do tutorials, attend a workshop like this. We have lots of recorded videos, but you can also just dive straight into a code base, and if you find something that you're not sure about, you can just hover your cursor over it, and it'll probably give you a pretty good explanation of what it does, some example code, and then it'll, of course, explain the type as well. So SnarkyJS is easy to learn, but it's also exceptionally powerful. And this is for two reasons. There's kind of two sides of this coin. One is Kimchi, which is our proof system. This is kind of deep under the weeds. This is the thing that actually makes the zero-knowledge proofs. And it has a number of features. Basically, it's state-of-the-art. But if you're into this kind of thing, if you're into cryptography, these are some unique features that Kimchi has. It has fully trustless setup, meaning that you don't have to do any kind of ceremony in order to create smart contracts or zero-knowledge proofs. Anybody who writes something in SnarkyJS can prove it, and nobody needs to rely on this, like powers of Tau ceremony or something like that. It has custom constraints for Poseidon, elliptic curves, and encryption. So this allows you to do operations that you'll have to do frequently, very efficiently. It also has a constant proof size, meaning that no matter how much computation you do, the zero-knowledge proof that you get out is always the same size. And it's quite small. It's also recursive. And this means that we can verify zero-knowledge proofs that were generated using Kimchi inside of other Kimchi proofs. This, when you couple it with the constant proof size, means that we can have, let's say, 5 proofs. Each one is the same size. And we can verify all of them inside of another proof. And that proof is the same size as each of the constituent proofs. So this opens the door to a lot of really interesting things. And this recursion is not just sort of linear, as in we can take one proof and put it inside of another. We can do arbitrary branch and merge operations, kind of. Finally, it's plonkish. And this, again, really just means that we're kind of like a part of an ecosystem of people that are developing new ideas, and that we can utilize their new ideas as you know, the whole sort of ecosystem works together. So again, this is not super important to dive into. Kimchi is not even a super important like thing to be aware of if you just want to build stuff. But if you're interested in the cryptography, you know, Kimchi is kind of like the cryptography engine that makes SnarkyJS work. So that's one half of the power. Again, this is what's under the hood. You don't have to worry about it too much. The other thing that makes SnarkyJS so powerful, though, is sort of the controls. It's the part that people actually interact with. You know, as a developer, you have to write stuff using this tool, and we've tried to make it as easy, expressive, and powerful as possible for you. The method chaining API lets you think through your programs in a linear way. This is a pretty big deal compared to you know, other zero-knowledge proof programming languages, where sometimes you have to think about things in sort of a way that, I guess, in such a way that there's no concept of time. This tends to be very hard for most programmers today. It's very old school. And so this method chaining API makes this pretty easy. You can see we have something like, let's do this one. We've got this variable is not red peg. We've got a guess at an index. We can check if it's equal to 0, and then you know, not this. So we want to know if guess I is not equal to 0. This is pretty straightforward. We check if it's equal to 0. If it is, we get a true. If it's not, we get a false. If it's true, then you know, we pass it into this not gate, and we get the opposite. And you can do this kind of over and over again. The result being that it tends to be pretty easy to think about, you know, here's my data, here's how it needs to change, and here's the output. And you don't have to worry about making sure that this is constrained too much. The other thing that we have is struct, and this allows you to define your own custom data types. This is, again, pretty unique to SnarkyJS. You can see up top here, we have myStructPure, which extends struct. Actually, let's do this bottom one, myTuple, which extends struct. And so we can pick, you know, we can make an array here and have a public key and a string in it, and this is a new data type. So this one is very simple, but we'll talk more later on about one that's more complicated. The idea behind this is that then once we have this struct, we can do whatever we like with it inside of our smart contract, and it just works. So yeah, instead of having to kind of worry about how your data is represented in real time, we have this layer of abstraction that lets you, you know, define how you want to interact with things before you go about interacting with them. Finally, plenty of the stuff that you need is already implemented inside of the SnarkyJS library. So what's included in SnarkyJS today? We have all sorts of types. Unsigned integers, 64 bits, 32 bits, integers of 64 bits, group, booleans, scale, public keys, private keys, signatures, and circuit string. And then with structs, you can, you know, compose these to create even more complicated data types. And we'll talk more about what these are under the hood in a little bit. We have efficient Poseidon hash function. Poseidon is a hash function just like, you know, Kachak or something, but it happens to be very efficient inside of our proof system. We have efficient encryption and decryption. We have efficient signatures. We have Merkle tree API, a recursion API, and also an action reducer API. Sorry, my watch just said hi. OK, so a common question that we get is, you know, why did we choose TypeScript? Lots of people have strong opinions about TypeScript. Really, the reason is because we're ecosystem focused. So the idea is that if you build user-facing products, you can leverage other people's work to build these amazing applications that do things that you might not know how to do, I don't know, like some kind of fancy cryptography thing. You might not know how to do like threshold signatures or something like that. So the idea is that, you know, you can import people's code and build these types of applications that depend on those primitives. And then if you are a cryptographer, we have plenty of support to help you build the tools for other devs. So you can talk to people like me and things like office hours. Mina Foundation has programs that can help you get paid to do this kind of thing. And the idea is that we want to have code reuse that's as high as it is in the JavaScript ecosystem. We want, you know, the people who want to work on hard crypto things to build hard crypto things and be able to, you know, get paid for it. And we want the people who want to build user-facing products to have doors open to them so that they can build kinds of products that were, you know, just simply not possible even a few years ago. OK, so how does it all work? Here's kind of an overview of SnarkyJS. This is very high level. And at the end, if people want to dig in more with questions, we can do that, or you can come stop me after. We also have, again, things like office hours. If some of this falls through the cracks, it's OK. The idea is for people who are interested in how we take a JavaScript program and turn it into a proof. This gives us a little bit of insight. So, OK, SnarkyJS is a TypeScript library. This is here just to sort of indicate that it's not some kind of like WASM compiler or something. It's not taking your TypeScript and compiling it into something else. It all is literally running in Node or Electron or a Chrome window. It is all literally TypeScript. And so what happens is when we write things using SnarkyJS, it feels a little bit like React using JSX, where we have this kind of like other syntax that's built on top of the JavaScript syntax that we're used to, but it is all ultimately JavaScript. And so how it works is we have a bunch of JavaScript types, and then we have some SnarkyJS types. And these SnarkyJS types are all ultimately composed of this type called field. And what field is it's an element of a finite field. This is like a math concept. It's basically a specific set of numbers. You don't have to worry about it too much. They're required for the underlying cryptography. But you have escape hatches so that you can use like unsigned integers or strings, things that you're familiar with working with. But what you have to know, just kind of like in order to orient yourself, is that under the hood, everything is turning into this field type. It's sort of like in a computer, when you use a string, ultimately it becomes an unsigned integer that gets represented as ones and zeros in a physical processor. Our sort of most fundamental representation of data is this field type. And so anything that we make in SnarkyJS has to be able to be represented in this field type in order for us to prove things about it. And so what this means is that the normal JavaScript code that we write, JavaScript doesn't know how to turn something like a JavaScript Boolean into a field element. But the SnarkyJS string type does know how to turn the SnarkyJS string into a Boolean. I'm sorry, into a field. And so SnarkyJS provides classes and functions that are compatible with this field types or the structs that are composed of them. Everything that we mentioned earlier, unsigned integers, Booleans, whatever, all of these are structs that are made using the field type. And so you can make structs of structs, so on. And so we have a bunch of classes and functions. Like one of these is circuit if, one of these is add. They do the simple things you would expect. But instead of doing these things on JavaScript types like numbers, they do it on fields or unsigned integers that are composed of fields. They do it on SnarkyJS types. And so SnarkyJS can represent any operation on these field types as a kimchi arithmetization, which is basically a math problem that mirrors what the program does. So the user doesn't have to worry about this. This is all done for you. You just write your program using the SnarkyJS classes and functions and using the SnarkyJS types. And as long as you've done this, then SnarkyJS afterwards can go on and introspect. It can sort of look at the code that you've written and figure out how to make a math problem that'll check it. And then finally, when a user interacts with the SnarkyJS program, they can call a method and generate a zero-knowledge proof that their interaction was legal. And this zero-knowledge proof is basically doing some additional math to this math problem that we have that represents our program and creating a proof or verifying the proof that comes out of it. Again, if this is kind of abstract or goes over heads, that's all right. Come talk to me after. There's a lot going on here, but all of it is under the hood. Users don't have to worry about this too much unless they're curious. OK, so how do SnarkyJS smart contracts work? Well, the developers write smart contracts in TypeScript, and they deploy the verification key to a zkApp account. On Mina, we have a bunch of nodes. We send a transaction. We sign it, and it has a verification key. And this verification key is basically a number that's committing to the smart contract that we've written. And so that then later on, the Mina network can verify transactions that are created for this smart contract using the verification key. And so if we were to change the smart contract code, the verification key would also change. Thus, if we say run a program correctly, but it's not the program that we committed to earlier, our proof just won't be valid. So yeah, the users run these smart contracts in their browsers or in Node or in Electron. Anywhere that JavaScript runs, these will run. And they generate a zero-knowledge proof of their interaction. So they take this zero-knowledge proof, and they send it to Mina. And if the Mina blockchain can verify this zero-knowledge proof, then we know that the transaction is valid and it goes through. And if the Mina blockchain can't verify the zero-knowledge proof, then we know the transaction is invalid and it just gets dropped. Yeah, of course. Yes, Mina only needs the key. So the circuit can live anywhere. You can put it in, OK, so I'll restate the question for everybody. So the question is, how does the Mina blockchain get the circuit, or I guess like the program? The Mina blockchain only has this verification key. Yeah, so the Mina blockchain has the verification key, and this commits to all of the functionality of the program that we wrote. The program itself can live anywhere. It can live on like a content delivery network. It can live on IPFS. It can live even on something like Ethereum. It really is just TypeScript code. And as long as you can get a hold of it and run it, the Mina blockchain doesn't even have to know what the code does. It just has to have this commitment to what the code does in order to be able to check that you ran it correctly. So the code actually does not go on the blockchain. It just lives wherever you want to put it. The only thing that has to exist on the blockchain is this verification key that's used to verify that the code ran correctly. Does that answer your question? You are in charge of the code that's used to generate the proof that then the Mina blockchain can verify using the verification key that's stored on the Mina blockchain. Oh, when the user sends their transaction, they're basically specifying this. Yeah, the same way that like when you call an Ethereum smart contract, you are specifying an address and then also a specific method. The same thing is basically happening with Mina. You're specifying which account you want to create a transaction for, which smart contract you want to interact with, and so that's how it knows which verification key is tied to your code. We can also come back to this later on if you want. So, OK, let's jump back into this. Sorry. So if the Mina blockchain can validate this zero-knowledge proof, then it commits any relevant state updates. Let me jump back one. OK, so yeah, if the Mina blockchain can verify the zero-knowledge proof, then it will commit any relevant state updates. So when we do something, we usually want to change the state of the world. We want to update a value, change somebody's balance, change a permission, something like that. And so when we run our smart contract method, we get a list of things that we want to do, a list of states that we want to update, et cetera. And we also get a proof that says we're allowed to update these states. And so we send just the proof and these updates to the Mina blockchain. And if the Mina blockchain can verify the proof, then we do these things. And so we pass into our smart contract some arguments that the user provides, the state of the smart contract at the time that we're running it, and the user can query this from the Mina blockchain. And then also some values from the state of the world. This can be something like block height. What we get out is a proof that we did this correctly. And we also get updates to the state of the smart contract and updates to the state of the world. All right. So that's how zk smart contracts work. But how do zkApps work? It's pretty simple. You can just install your smart contract into your UI repository and deploy it. So yeah, you can publish it to GitHub. You can publish it to NPM as a package, whatever you want. And then when it comes time to use it in your UI, it's just TypeScript code. So you just import the smart contract methods that you need to call directly into your front end. Then the user does something in your front end. The front end calls the appropriate method in the smart contract and creates a proof. And then we send this proof off to the Mina blockchain. So all of the code runs in the front end, and the only thing that lives on the blockchain is this verification key, which is used to verify that we ran the code correctly in the front end. OK, so now let's talk about the Mina protocol. What is Mina? It's a layer 1 blockchain that proves its entire finalized state using recursive zero-knowledge proofs. So other blockchains increase in size as more transactions are added. A blockchain like Ethereum needs to remember every single transaction that's ever happened in order to be able to verify that transactions that have happened recently happened correctly. So as time goes on, Ethereum scales not only with the number of accounts that people are in control of. It also scales with the number of transactions. Mina does not. It stays 22 kilobytes, a fixed size. And so we can get into a little bit of what this means. Basically, Mina does not have to remember all of the historical state. And the reason why is because instead of using this kind of a bunch of signed transactions and then a pre-agreed way to evaluate these transactions, and then a bunch of game theory because we do them all in the open and remember all of them, Mina uses cryptography directly to verify these transactions. So it uses zero-knowledge proofs instead of game theory. So is this just cool, or is it actually useful? The answer is that it's both, and for quite a few reasons. The first is privacy. So on Ethereum, smart contracts run on every single node, and so all of the information is inherently public. If we have an Ethereum blockchain here and an Ethereum smart contract and we want to call a method, we call the method, we specify the arguments that we're passing in, and then we send basically this call and the methods, and the arguments that we want to pass in to every single Ethereum node. And every single Ethereum node evaluates these in public all at the same time. And so this means that it's very hard to build private applications on Ethereum. If you want to build private applications, you have to find a way to obfuscate data that's inherently public to such a degree that it's effectively private. And this usually involves really complicated cryptography. So Mina smart contracts run in the browser. And this means that the arguments and the intermediary values are private by default. So if we want to run a Mina smart contract method, we call the method and we pass in the arguments on our local machine. And what we get out is the relevant updates as well as a proof. And so we send just this proof and the updates to the Mina blockchain. And Mina will verify the proof and then update the state on chain if the proof is valid. And so this proof doesn't disclose any information about the computation that we've done. OK, so we have privacy, and we also have scalability. There's no gas model. zkApps run off-chain, and so the amount of computation doesn't affect the transaction cost. If we do a lot of computation, it might take a little bit longer for our browser to run the method and generate the proof. But the proof that we get out will be the same size and the same computational complexity to verify. So if we want to do a tiny bit of computation, that works. And if we want to do a ton of computation, that works. We just might have to wait longer, but it'll be on the user's machine. Once the proof goes to the blockchain, it will always take the same amount of time to verify, no matter how much computation you do in it. So you can actually do an unlimited amount of computation in a Mina transaction. And in fact, the Mina blockchain itself is kind of an example of this. We're doing basically an unlimited amount of computation and attesting to the fact that it's correct using this single proof, which is tied up in this 22 kilobytes that we talked about earlier. OK, so this works great if you have transactions that do a lot of computation. But what if you want to build applications that do a lot of transactions? In this case, it's possible for developers to use recursion to build these things we're calling application-specific rollups. And these are basically what they sound like. If I have something like a game, let's say I have a 2-player game, and I want to play this game let's say I want to build this game in like the most naive way possible. I would build a smart contract where when I want to make a move, I call a method. And when you want to make a move, you call a method. And we go back and forth like this. This works fine. This is how everything works on every other blockchain right now. But the problem is that we have to wait for a block to be mined, and we have to pay a transaction fee every time we want to make a move. With Mina, this can work much differently. Because the smart contract execution is verified using cryptography instead of game theory, we can have the whole blockchain validate some computation, but in many cases we don't have to. In the case of something like a 2-player game, the only person who really needs to check that I'm playing the game correctly during the course of the game is my opponent. Right? In theory, they should have an incentive to not let me cheat. If they do let me cheat, then the game is pointless. So what I can do is I can actually write the smart contract in such a way that I make a move, I create a proof that my move was valid, I send my opponent the proof, they verify the proof, and then they make their move. And when they make their move, their computation for their move will actually also verify the proof of my move. And so we can go back and forth this way, exchanging these proofs. And the proofs don't grow, right? I send you a proof of a fixed size. You make your move and send me back a proof of fixed size that attests to your move and my move. And then I make another move, and now I have a proof that's still the same size, but it attests to 3 moves. And we can do this over and over and over again until eventually we reach an end state. And once we have, a complete game, a proof for a complete game, then we can actually send this into the Mina blockchain and pass this proof as just an argument to a smart contract method. And so we can pass a proof that says, hey, I won, let's pay out, I don't know, some reward to me. So yeah, there's a lot of other ways that you can kind of extend this model. This is fairly complicated, and actually this is just the very beginning of a sort of series of workshops that will explain how to build a Mina application from nothing to something that's pretty polished and has sort of touched all the bases, so to speak. So we'll talk much more about this. We'll actually have a session of this workshop. So the subsequent sessions will be remote. You can watch them online. And we'll have a follow-up session that will talk about how you can build an application-specific rollup for the Wordle game that we're going to build today. Okay, so we have privacy and scalability. Usually, these come at this cost of decentralization. However, for Mina, this is not the case. Because it's possible to validate the entire finalized Mina state using only a small zero-knowledge proof, and I'll kind of maybe touch quickly before we jump in any more on why this is possible. So the way that Mina works is that we have a bunch of transactions, and these transactions are zero-knowledge proofs. And then we have our consensus mechanism, and this is something that we can also prove using zero-knowledge proofs. And so what we do is we take a bunch of transactions that are zero-knowledge proofs, and we verify them, and we also verify that they have been sort of processed correctly, that states and stuff have been updated correctly. And so we have all this computation of verifying the proofs and doing the things that the proofs tell us to do. And we can verify all of this information in another proof. And then when it comes time for us to do more stuff, when we have more transactions, we can take this last proof, verify it, verify all the transactions, and verify that we've done everything correctly, and create a new proof. And then we can forget about the last proof. And so in order to know that the current finalized Mina state is correct, you just need to verify this single proof. What that means is that you can verify this proof kind of anywhere. It's pretty easy to do. It doesn't require a lot of storage or networking overhead. And the end result of this is that there's not really a reason to rely on trusted third-party node operators. This is another team in the ecosystem. They are called Viable Systems or Viable Labs, I forget. But they're working on something called Open Mina. There's actually a demo of this that exists today, and it's linked to at the end with this QR code. So what is this? This is a full Mina node that runs in the browser. You can go to this website, send a transaction today without connecting to any kind of RPC endpoint. Literally everything happens in the browser. We start some stuff, we get it all ready, we connect to some other nodes, and then we catch up to the network. And this all happens in less than a minute, and then we're ready to send transactions. So you can imagine this can be built into mobile applications, it can be built into browser plugins, and it can be built even directly into websites themselves. We hope that this will result in a network that is substantially more decentralized than anything that really exists today. It's quite a different way of doing things. Okay, so if Mina is so, yeah, go ahead. Yes, okay, this is a good question. And also, yeah, I'll just say ahead, with anybody that has questions, jump in. Usually these presentations are a little bit sort of smoother, but this one, the idea is that, yeah, the idea is kind of that it's pretty hands-on, and anybody who has, we'll kind of talk about whatever people are curious about. So we talked about these nodes. We talked about 22 kilobytes. So what is this 22 kilobyte thing? What it is it's the proof for, it's the Mina proof. It's the state root of Mina. So we have a Merkle tree that is committing to all the data. and we have a root of this Merkle tree. And so the proof basically says that this Merkle root is correct. The Merkle root attests to all the information downstream of it. And then what we also include in this 22 kilobytes is a path down to a single user's account and all the information that's stored in it. And so what that means is that with 22 kilobytes, we can store everything we need in order to know that Mina is working, and we can store all the information that's relevant to ourselves. So what that means then is that if I want to go talk to somebody like you and send you a transaction, well, you have all the information for yourself, I have all the information for myself, we both have all the information for Mina, we can construct a transaction to, let's say, do something simple, like transfer funds between each other. That's what the 22 kilobytes is. And so this is all that's needed for something like one of these web nodes that we looked at earlier, right? It's only concerned with one account. There's another kind of node called a block producer node. And this type of node records the state of all the accounts, but it doesn't store any history. And so the reason that it doesn't store any history is because it doesn't have to. It knows that all of these states are correct based on the zero knowledge proof. It doesn't need to be able to sort of like sum up all the historical transactions in order to know that the state that we're at today is the correct state. So these block producer nodes are named accordingly. They're able to produce blocks because they know everybody's state. These nodes grow based on the number of accounts. They don't grow over time. And so what that means is that there's kind of like there's a place where it plateaus. There's a point in time where people don't need more accounts. There's a limited number of people. Even if they're interacting constantly, we can forget about the history of their interactions. And so these block producer nodes are still very small. They're a couple of gigabytes. You can start one in less than an hour, and you can be producing blocks. And they won't, oops. Hopefully it comes back. Yep, OK, we're good. There we go. OK, so we have block producer nodes. The final kind of node that we have is called an archive node, and this does what it sounds like. It stores every single account and the history for every single account. These are useful for things like block explorers, people who want to do like analytics, that kind of thing. And so these block producer nodes store everything and expose it all through a GraphQL. So hopefully that answers the question. We have kind of three kinds of nodes. One node has everything you need for a single account. Another kind of node has everything you need for every account. And a third kind of node has everything you need plus all the history of everything that's happened. I will continue to jump forward then. OK, so if Mina is so easy to verify that we can do it in a browser, can we do it in other places? Could we do it in like a smart contract, for example? I'll get to you in just a second. Because Mina is so easy to verify, it's actually possible to write smart contracts on other blockchains that can verify the Mina state proof, and as a result, bridge the entire Mina state over to their ecosystem. So yeah, smart contracts on other chains can bridge the whole Mina state just by verifying the most recent proof. We have another organization in the ecosystem that's working on this. They're called the NIL Foundation. And they're building in EVM Mina state verification and also a bridge to EVM chains. So there's also a demo of this live. A lot of this stuff is very close to finished. And so what we can do is we can take the information from Mina. This is going to be the state root, the proof, et cetera. And we can build an auxiliary proof, which is just a proof that's more efficient to verify on Ethereum. This takes maybe a minute on a MacBook Pro. And so we get our auxiliary proof. And then we can pass this auxiliary proof as an argument into a smart contract on another blockchain. In this case, we're using Polygon Mumbai, but you could do just as easily on Ethereum. And so we send this transaction, and the transaction gets mined. You can see it costs 9 cents on Polygon. And the end result of this then is that the whole entire Mina state, or a commitment to the entire Mina state, is bridged over to this blockchain. So now people who have smart contracts running on Polygon can, if they want to access some value from a Mina smart contract, they can basically, pass in the Merkle proof down to this chunk of information that they want from the Mina smart contract, and then, verify that this is valid according to the state root that we have in our bridge contract, and we can interact with this information on Mina. This is a much different way of bridging because it doesn't require any sort of like locked capital or anything. It's instantaneous. As soon as we pass the proof in and the transaction is mined, all the information is bridged over, and also anybody can do it. So you can have sort of a situation where, if I have some sort of arbitrage or something I want to do, and I have an incentive to update the information to the most recent values, I can just call this method straight before I do my arbitrage or something. So the answer is that this will also include the timestamp. So the Mina smart contract the smart contract on Ethereum will also have the timestamp for it'll have the block height for the Mina blockchain. And no, I'm sorry, I meant to say block height.
So I can just do it now and push a Mina root from last year.
Well, no. So the block height would have to be higher than the last the last block height that it verified. Okay, sorry, and then I'll also get going a little bit quicker, just because I've realized we're behind a little bit. But somebody back here had a question. I'll answer very quickly, and I'm also going to take a drink.
I think it isn't. Oh, it is. Nice. Hi.
Hey.
Thank you for telling us all this stuff.
Of course.
So I think I understood now that apart from this very small proof, there's a state somewhere.
Yes. The state lives on the Mina block producer nodes, but it's also not coupled to. This is something we should talk about. I'll talk more about this at the end. The state is not sort of inherently attached to the computation in the way that something like Ethereum requires that it be. So the Mina nodes can store state, but you can also put state somewhere else. Like, for example, if you wanted to have a lot of your state stored like on the user's machine locally, you can do that too, and you can just have your smart contract store like a Merkle root that's committing to all this state.
So I could have my own node running in the browser and publish my proofs, but never publish the state.
Yes. Well, so it depends on what kind of state.
So the block explorer, no block explorer could analyze my transactions because I never published them.
Yes, you can do this, but not. There is state that's stored directly on Mina. So you could do something like this. You could have state that's stored directly on Mina be used to store a Merkle root for a bunch of private state that you could store yourself. And then the Merkle root will not reveal any of this private information. And then you can do what you want to with this private information and prove that you're altering it, that you're augmenting the information in ways that are allowed according to some set of rules that you define in your smart contract. And then as you make these changes, the Merkle root will update. And so you'll update the Merkle root on chain. But the Merkle root won't reveal any of the information that you're storing locally. Does that make sense?
I think it does.
Yeah.
But I cannot transfer Mina without exposing who is part of this transfer.
This is true this is true if you don't build anything in addition to what we've built. But because it's so easy to use zero-knowledge proofs with SnarkyJS on Mina, it's very easy to build mechanisms that would allow you to do something like shielded Mina transfers. Yeah, and so we can talk more about this. Basically, all of the state is public by default, but it's very easy to use this state to commit to private state. Yeah, and so the state has to be public, right? Because it's otherwise you can't come to consensus on it. The key is that the computation can be private, and so this opens the door to all sorts of stuff. But I'll jump back to this at the end. For now, I'll kind of keep going forward. So oracles. Because SnarkyJS smart contract methods can accept and validate signed data, and because this happens on your local machine, it's possible to ingest verified data privately. So this means that like if I have some service that will provide me with a signed credit score or something, I can grab this from that service and I can pass it directly into my smart contract. This also means that it's possible to ingest a lot of it. You can ingest rich data using SnarkyJS. So as opposed to having like an oracle that stores like the price of a token or something, you can dump a whole like JSON response into a SnarkyJS smart contract. In fact, we have I guess a friend who's working in the ecosystem who's built a JSON parsing library. Okay, so we can ingest data privately, and we can also ingest a lot of it. And in the future, zk oracles will allow users to verify data from any HTTPS website or API. So right now, you have to have somebody sign this data. This can be the person who's providing you the data. It can be some sort of trusted middle party. But in the future, it'll be possible to basically grab any data from any website or API that's returning the data through an HTTPS connection and verify that this came from the domain that claims to have sent it, and then we can pass that information into a smart contract. So we can do something like go to a website, grab a value that we want to pass into a smart contract, and then pass it in a provably sort of correct way. Okay, what else do we have? Well, we actually don't know everything that's possible yet, and so that's why we're hoping that people like everyone here, build cool things, talk to us, and yeah, we're kind of building the foundation and hopefully opening a lot of doors, and we're excited to see what people end up doing with it. Okay, so now we have our Hello Wordle part of the presentation. We'll talk about a smart contract and build it together. So if you haven't yet, install Node.js and npm, npm install -g the zkApps CLI, and clone the GitHub repository. For people who don't know, Wordle is a game where there is a secret word, and we try to guess what the word is. And when we make a guess, we get gray tiles if we've guessed a letter that's completely incorrect, as in it's not the correct letter and it's not in the correct place. We get a yellow tile if we've guessed a letter that is in our word but is not in the correct place. And we get a green tile if we've guessed a correct letter in a correct place. And so we have a limited number of turns to try to guess what the word is by sending a word, getting some hints in a response, and then guessing another word, and so on and so on. And so here we guess bears first. We can see that R is a correct letter, but it's in the wrong place. Then we guess groof. We can see that now R is in the correct place, O is in the correct place, O is in the correct place, and F is in the correct place, but G is not in the word. And then eventually we guess proof, and that's the right word. So we get all green tiles, and we've won the game. So there's a few things to keep in mind for this. The first is that this is generally played as a one-person game, but in this case, we're going to build a smart contract for 2 players, and one player will be the sort of the word guesser, the standard player, and the other player will be a hint generator. And the reason why it makes sense to have 2 separate players for something like this is because if you were to build this as a one-player game, your machine would have the secret word in it, basically, and so you can find out what the word is, right? Like, in other words, your browser would contain the word that you need to guess. So it makes sense to build it as a two-player game. And then if you want to play it as a one-player game, you would have a third party. It could be a service that would play the game against you. So for this, we're just going to build the smart contract. The rest of the app will be coming soon. And we'll have, like I said, another workshop on that later. So we'll talk about the structure of the smart contract really quickly. And you can open up the source Wordle struct file on your computer if you're interested in following along. First, we have kind of like a preliminary thing. And so don't worry too much about this. This is defined at the top above our smart contract. And this is a struct. So we're creating something called Word by extending struct. This thing called Word stores encoded Word, which is an array of 5 field elements. And so we've defined a way to store one of these Wordle words using field elements now. What we also have is a static method from string, which we can pass a JavaScript string into. And when we do that, we'll convert that string to be all lowercase. We will increment through each value in the string. We'll use this regular expression to test if it's a letter. And if it is a letter, then we will push this onto our encoded word array as a field. So we'll take the character code for the word, minus 96. This just gets us values between 1 and 26 for the letters of the alphabet. We pass this into field in order to create a field of this value. So we're passing a JavaScript number into the field, and we're getting a field of the same value. And then we're pushing this onto that encoded word array. If the letter's not lowercase, or if it's not a letter, if it's like an ampersand or something, then we just push a 1 value, which is an A character. Then finally, we return a word that includes our encoded word that we just created. So what that means is that we can call, word dot from string, pass in a string, and we get back a word that represents it. We also have this other method here, hash, and hash will return the hash of this encoded string. So you have this Poseidon function. we have this Poseidon object. And oops, I'm sorry about that. Let me make sure that does not happen again. Okay, so we have this hash function, and we're going to pass in our encoded word. The hash function accepts an array of fields, and out we get a hash, which is a single field element. So we've made a struct that's going to make it easy to work with words in our smart contract. It takes JavaScript words and represents them as field elements. Now, we'll talk about the structure of our smart contract. So we have this thing, smart contract, and we extend it into Wordle. So we've now created a smart contract called Wordle. And the first thing that you'll notice is these 3 state decorators at the top. These are used to tell Mina that these are variables that we want to store in the state of the Mina blockchain. We want Mina to basically store these in the blockchain and then check that when we're updating it, that we're updating them in a valid way. And so we have one called solution hash. This is a field element. We have one, and yeah, field elements, I think I mentioned this earlier, but they're basically for when you're kind of just getting started, they're really the same thing as unsigned integers. There's a couple interesting properties that they have, but they're very similar to numbers you're used to. One of the properties that they have is that you can't really call like a mod method on a field element. It doesn't make sense. There's not like a way to do modular. They're kind of inherently doing this already. So in this case, we have a turn number, and we want to be able to check whose turn it is by turn number mod 1. And so we use this unsigned integer of 32 bits. And this is, again, under the hood, comprised of a field element, but it has some extra logic that allows you to work with it just like you work with the unsigned integers you're used to. Finally, we have this word object. We have this word type that we defined earlier using the struct. And so this will represent the last guess that we made, and it will also store the hints that the user creates. That the hint generator creates. Then we have an init method. This is a method that will run before users interact with the smart contract, and we'll talk about that in a second. We have a publish guess method, which will take in a word as an argument. So this does what it sounds like. We call it when we want to publish a guess. And then we have a publish hint method. And this also will take in a word, but this word won't actually be the guess. It'll be the secret word. And it's OK to pass in a secret word as an argument to this method because it won't ever actually leave your machine. Finally, we have, I'll kind of talk briefly about what these decorators are. This method decorator basically tells SnarkyJS that this is a method that users are going to call. The state decorator basically tells SnarkyJS that this is a state that should be stored on the blockchain. So these decorators are a part of TypeScript. They, I think that it used to be called @script. I think that this used to be in 2 separate projects. But these are just like Python decorators. I can talk more about them with you after if you want. But what they basically do is this tells JavaScript, hey, take this, pass it into a function, and then whatever comes out of that function, put in place of this chunk of code. OK. Yeah, I think that's a good way to characterize it. Yeah. OK. So we've got this init method. I said earlier that this is something that we'll call before users interact with the smart contract. We have super init. Don't worry about that. That does what you'd expect. And then we have some initialization. We want to set all of the variables, all of the state variables that we defined earlier to initial values. And so this init method should be called before any user interacts with the smart contract. In other words, immediately after deploying the smart contract, we should call this init method. And so when we call the init method, we will take this solution hash, and we'll call this set method on it. And what we'll do is we'll set it to a word from string hello, and then the hash of that. And so we take our word hello, we generate a word from it, we get the hash of that using this hash method that we defined, and then we pass that into set for this solution hash. And what that does is it sets the solution hash on the Mina blockchain equal to this value. Next thing we want to do is set the turn number to 0. So we'll create a new unsigned integer of 32 bits. We'll set it equal to a field, which is equal to a JavaScript number that's 0. So we'll get, basically, JavaScript 0 turns into field 0 turns into unsigned integer 0, and then we set this to turn number. And then finally, we'll set the initial guess. And so we'll just make it AAAAA. And it won't be possible to generate a hint until the guesser updates this. So it doesn't really matter what this is. We're just initializing it, I guess, because it's good practice. So we do the same thing. We get a word from string and set it equal to last guess. So again, this method should really only run once, right after the smart contract is deployed, and then nobody will run it again. Next, we have publish guess. And so we'll talk about what this is going to do, like how do we do this. The first thing that we want to do is grab the turn number from the Mina network. So because our smart contract runs locally, we need to grab the number from the network before we can do things with it. The next thing that we're going to do is we're going to check that it's the guesser's turn. And so we can use the turn number to check if it's our turn. After that, we will increment the turn number. Then we'll check that all of the values that we passed in our guess word are between 1 and 26. In other words, that they're valid letter configurations. That way we can't guess a word that the hint generator can't generate a valid hint for. And then finally, we'll set this last guess state to our new guess. So first things first, we'll grab the turn number from the Mina network. So we'll make a variable turn number, and we'll set it equal to, turn number get. This get method will, contact the Mina network, grab the value for turn number, and then we'll dump it into this local variable. The next thing that we'll do is we will assert that this turn number, that means the turn number variable in the Mina network, is equal to turn number in our local runtime. And so this line is kind of interesting. It is necessary because the smart contract runs, outside of the context of the blockchain. And so what that means is that let's say that we were to do something like grab a turn number, run this method, grab a turn number at one point in time, and then wait like a day. And by that time, the turn number had changed. Somebody else had changed it. Well, then our proof is valid, but it's not valid for the current time anymore. Does that make sense? Like, it's valid assuming a precondition that is no longer true. And so what this assert equals does is it checks that this condition is true at the time that the proof is accepted. So in other words, this top line grabs the number and does stuff, it grabs the number at runtime, and then this bottom line checks that the number that we used at runtime is the same as the number on the network when it comes time to verify the proof. Yes, that's correct. Yep. Okay, so then what we'll do is we'll check that it's the guesser's turn. So we'll take turn number. This is our unsigned integer. We have this mod method for it. We'll call mod 2, so we'll get, I think 0 if the turn is even and 1 if the turn is odd. I might have got that backwards. But then we'll call this assert equals method, and we'll pass in an unsigned integer that's of value 0. And so this assert equals method basically, what it's doing is it's saying that unless this condition holds true, unless turn number mod 2 is equal to 0, it should be impossible to generate a zero-knowledge proof. And so in this way, if we try to run this method on the wrong person's turn, what we'll get is even if we can run the method locally, we will not be able to generate a valid proof for it. The final thing that we'll do is we'll increment the turn number. We'll call this set method, does the same thing as it did earlier, and we'll pass in turn number, but we'll add to this turn number an unsigned integer of value 1. And so the turn number will be incremented, and then we will check that all the values are between 1 and 26. So we just have this for loop. We're going to grab, guess. So this is our word that we passed in. We're going to grab values from this encoded word, and then we're going to call the assert method on them. So these values will be fields, and the field type has this assert greater than, equal to, less than, greater than or equal to, etc. methods attached to it. And so we can assert that it's greater than or equal to 1 and less than or equal to 26. And we'll do this for each index in the array. And the result then is that we know, again, if we find some way to pass in a value that's not really a letter, a value that doesn't make sense, it just won't be possible to make a proof, and so we won't be able to update the state. The next thing that we'll do is we'll set last guess to the new guess. So this is pretty simple. We've got our guess. We've checked that it's our turn. And now we can set the guess on chain. So we'll take our last guess, and we'll set it equal to the new guess that we passed in. So that's one half of the interaction. This is what the guesser does. Now the other half is what the hint generator does. And this is a little bit more complicated, but it's basically the same idea. We have this publish hint method. We pass into it a word, which is our solution. It's actually the secret for, it's the solution word for the game. And the top part of this is very similar to what we've done before. We're going to grab the turn number from the Mina network. Same thing as before, turn number, get, set it equal to a variable called turn number, assert that the turn number that we use at runtime is equal to the turn number at the time that we validate the proof. And then we're going to add 1 and mod to check if it's the hint generator's turn. So we'll take the turn number, we'll add 1, we'll mod 2, and it should equal 0, right? The idea being that this is the opposite of what we checked earlier. By adding 1, we are checking that it's we're checking, this will be true only in cases where this similar chunk of code for the other method would be false. So yeah, this is doing the opposite of what our turn number check did for the publish guess method. So that we will only be able to run this method if the guesser has just guessed, but the hint generator hasn't generated a hint yet. The final thing that we'll do is we'll increment the turn number again. Same thing as before. We take the turn number, we add 1 to it, and then we set it on chain. OK, so what do we do then? We have to check that the solution that we provided, that we passed in as an argument, is correct, right? We want to keep it private, so we don't want to store the solution on chain, but we still want to be able to check that we're not changing what the solution is every time that we, generate a hint, right? Because you could make the game unwinnable that way. So what we do is we grab this solution hash that we stored on chain, and this is a commitment to the solution that doesn't reveal what the solution is. And we assert that the solution hash is equal to the solution hash, just like earlier. So we check that the value that we grabbed when we run the code is the same as the value that exists on chain when we validate the proof. And then what we do is we check that the solution hash is equal to the result of calling the hash method on our solution that we passed in. And so now we know that from turn to turn, we're not changing the solution. In other words, we're always passing in the same solution value because we can check it by hashing it and then comparing it to the hash that we've stored on chain. So all of this is checks. We're checking that it's our turn. We're checking that the solution that we provided is valid. And now we can actually grab the last guess, the guess that the last player submitted. Again, this should look pretty familiar. This is basically the same thing again. And we can actually go through the process of generating the hint now. This is the most complicated, interesting part. And so first we want to check if we have any green hints. We want to check if there's any green letters. These are letters that are the correct letter in the correct place. What we can do is we can have this for loop that runs through every index in the array, and we're going to check if the letters at this index match. So we have is correct position. This value will be a Boolean, a SnarkyJS Boolean, and it will be true if the value in last guess at index I is equal to the value at solution in index I. And so this equals method is different than the assert equals method. The assert equals method just makes it impossible to make a proof unless it's true. The equals method returns a 1 or a 0. It returns a Boolean. So if the guess and the solution have the same letter in the same place, then this will be set true. Otherwise, it will be set false. And so if the letters match, then what we're going to do is we are going to add 200 to the letter. This way, we still keep basically a representation of what the letter is, right? Because it's a value between 1 and 26. But we get a 2 in front of it if it's a correct, if it should be marked with a green hint. The idea being, like, if we have z and z is correct, then we'll take this 26 and we'll increment it to 226. And so then the guesser can look at this and say, hey, this is a z and it is a correct letter in the correct place. We got a 2. So what we do there is we use this circuit if method, and we pass in is correct position. So this is true or false. If it's true, then we add 200 to this value in the last guess. And if it's false, then we just set the last guess equal to what it was before. In other words, we do nothing. Yes? If it's OK, do you mind? I think I only have a couple minutes left, so do you mind? We'll go back to it at the end. Sorry about that. OK, so we've got our green letter hints. Next up, we have to check for our yellow letter hints. These are hints that are going to be for letters that are included in the word, but were not guessed in the correct position. So this time, we have a nested for loop. We're going to iterate through every value in one word, the guess, and every value in the solution. And so what we'll do is we'll check if the letters at these indexes match. If they do match, we'll set does letter match equal to true. And then if the letters match, we'll also add 100 instead of 200 this time to the value. So this is the same thing again. We have our last guess. If the letter matches, we add 100 to it. If the letter doesn't match, we set it equal to itself. But in order to not count the values twice, what we have to do is set the values in the solution to 0. The reason being that this way we only count the correct number of letters in the wrong position once. Does that make sense? Otherwise, you would iterate through and count them multiple times. So we want to sort of like check off that we've already counted that these letters match after we've done so. And so this time, what we do is we have the same thing, but for solution, and we use this circuit.if. If the letter matches, we set this solution value equal to 0. Otherwise, we set it equal to itself. And so the idea then is that if we count the letter, then we set the solution value equal to 0, so that then we can't count that letter again. Because 0 represents nothing. It doesn't represent any letters in this case. And so nothing in the guess will match it. We check to make sure that the guess doesn't have any zeros in it. So once that's done, what we get is we get this last guess. And now it has values that either equal the same thing that we passed in. So like 1 would equal 1, 5 would equal 5. Or it has values where 5 is turned into, say, 105. Or 12 is turned into 112, meaning that this letter is a correct letter, but it's in the wrong place. Or if we have a correct letter in the correct place, then we've added 200 to it. And so we get 10 would turn into 110 if we guessed that, if that letter was a correct guess in the correct place. Okay, so the final thing that we do is we take our last guess and we set it equal to, we take last guess on chain and we set it equal to the last guess that we just generated. And so what this does is it updates all of the hints on chain so that then the user, the guesser, can go and look at the hints and check whether they got any correct, whether they got any green or yellow hints, and then they can use this to generate a more informed next guess. And so this exchange goes back and forth until either a turn number is hit, which we didn't implement here just for the sake of simplicity, or until the user generates, until the user guesses the correct word. Okay, so now we can test it. What you can do is you can save your file, and you can run npm run test. And when you do, you should see something that looks like this. You can see on turn number 1, we are going to guess the word exile. This means that we're going to set guess equal to 5, 24, 9, 12, 5. That represents exile. You can see E is the 5th letter in the alphabet, and this last guess starts with 5 and ends with 5. And then we increment to turn number 2. And we'll guess, exile is still the word that we guessed, but this time we've taken 5 and we've incremented it to 105 because E is a correct letter, but it's in the incorrect place. We can see that we've taken L, which is 12, and we've incremented it to 212 because L is the correct letter in the correct place. And you can see that 5 has not been incremented. We did not count it twice. So even though there isn't E, there's only one E. So this stays 5 while the first one increments to 105. So now let's guess hello. This is the correct word. So we'll take this value, use it to determine what we should guess next. We can see, hey, hello's got an E in it. It's got an L in the right place. Let's try hello out. So we encode hello as 8, 5, 12, 12, 15. And then when it comes time for the hint generator to look at it, every single letter is in the correct place. So we get 208, 205, 212, 212, and 215, meaning that we've guessed the word correctly. Okay, that's that. Congratulations, you've just built your first ZK app. If this seems maybe not so satisfying, that is why we have we will have more remote presentations in like a live stream form that will explain how to build the front end for this, how to build a recursive rollup that that proves the same game without having to send transactions to the blockchain every time. And then also, we have Mina Foundation is running something called zkIgnite. It's cohort 1 right now. It's not too late to submit a proposal and get funded. zkIgnite is a program that will help connect developers or people who are sort of entrepreneurial, designers, whoever, with funding, technical mentors, etc., in order to help them build things on Mina and get them off the ground. There is 500,000 USDC and 500,000 Mina tokens that are available in cohort 1. It has a very unique governance structure that you can learn more about in a blog post. It should be at this QR code. And this is a great way to get involved. You can also talk with people like me about technical stuff in office hours, all sorts of interesting things. The other thing that we have is this Notion page, and this will have links to everything we've talked about in the tutorial, links to zkIgnite, links to our Twitters, Discords, links to the GitHub, all that stuff. With that, thank you so much for attending. I'm sorry it was a little bit hectic. Oh, we've got one question? Okay, yeah, let's do a question.
Hi. Somehow I missed the zero knowledge part of the application.
Who has the microphone?
Here,
Oh, go ahead.
I somehow
Oh, do
missed.
you not have a mic? Yeah, go ahead.
I hear myself. Do you hear me?
No, I couldn't. But now I can.
I somehow missed the zero knowledge part of the application. Because the checker knows what the guesser has guessed.
Yes, but the guesser doesn't know the secret word. Does that make sense?
Yes,
So
but not through zero knowledge, because he knows nothing. He has to trust the other party.
No, he does not have to trust the other party when they generate the hint. So if so let's say that we were the hint generator and we tried to generate an incorrect hint.
Yes.
These assertions would fail. So for example, like let's say that I tried to add a 100 someplace where it didn't belong, or I tried to not add a 100 someplace where it did belong. Because doing that would diverge from the way that this code was written at the time that we created the verification key, it would be impossible to generate a valid proof for that update. Does that make sense? So if at the end of this, running this method, what we get is basically a request to update last guess on chain. But we can only send that request if we have a valid proof. And we can only get a valid proof if we've done everything like these add and if statements and equal statements correctly. So in other words, even though because the user runs this publish hint method on their machine, they don't disclose the solution that they pass in. But because we check that the solution matches a hash that we store on chain, we know that the solution that they pass in is valid. And then we also know that all of the work that they do in order to generate these hints is done correctly. Does that make sense? If it doesn't, we can also talk more about this after. I'll stick around in like the back corner.
All right.
So for anybody who has more questions, I think I should probably, I'm about 3 minutes over. So I'll hop off the stage now and just say thanks to everybody. But yeah, the idea is check out zkIgnite. Tune in to the future sessions of this workshop. Hopefully they'll be a little bit smoother. And come talk to me in the corner with any questions that you have. I'd love to answer. Yeah, that's about it. Thank you so much for coming. And I hope you guys have an awesome time.